Hello everybody, we are going to continue our exploration of two-variable data by looking at scatterplots and correlations. So today we start actually looking at quantitative measurements, but looking at two quantitative measurements as our variables. Our EQ for today is what is bivariate data, and then how do you verbally and graphically describe a relationship in bivariate data? Because ultimately that's what we want to do. We want to be able to describe a relationship between two different variables for any given individual. Now, throughout this lesson, in your practice, you may want to start looking at this website, alcula.com, which has all kinds of great online calculators, including one that will make a scatter plot for you. So, if you don't want to make things by hand, you want to make a computer-generated one, that website might help you out. Now, what is bivariate data? Well, it seems to make pretty clear sense that bivariate data, bi as in two, will represent two variables. So it's just our fancy math stats word for saying two variable data. We say bivariate data. So it includes two variables that describe an individual or things. Now, what's important about this is that each individual has two values associated with it, one for each variable. An example might be height and wingspan among stats students. So we would want to make sure we understand that each individual is going to have a measurement for each height and wingspan. Now, often we want to find the nature of the relationship between these two variables. Essentially, what we are asking ourselves, does one variable explain the other? So in this case, I might want to know, if I know somebody's height, is that explaining how long their arms are? If somebody's really short, does that mean they have longer or shorter arms? If somebody's really tall, does that mean they have longer or shorter arms? Understanding the nature of the relationship by examining bivariate data will help us answer that question in a mathematical sense. Okay? Now, response variables and explanatory variables are the two kinds of variables we will be looking at when we examine bivariate data. The response variable measures the outcome of a study, and we call that the dependent variable. Now, dependent variable, that's just your fancy algebra way of saying that's the y variable, which means a response variable is going to go on the y-axis. So, the outcome of your study is going to go on the y-axis every single time. Now, the explanatory variable is the thing that may help explain or predict changes in that response variable. And from algebra, we call that the independent variable. And we remember the independent variable is the thing we plugged in to find y. That was our x value. Okay? And the way that I can remember that is explanatory is the x variable. Okay? So your explanatory variable will always go on the x-axis. Now, what do we call this kind of graph? Well, we call it a scatter plot. So a scatter plot is your graph for bivariate data. No histograms, we don't call it a line graph, no pie charts or anything like that, no box and whisker plots when we're talking about bivariate data, we talk about scatter plots. It's the best way to display relationships between two quantitative variables outside of just looking at a list, because this will put a very nice visualization on that relationship. In a scatter plot, each dot represents an individual and shows a value for those two variables. That means that each individual is an ordered XY pair. Now, in this example, I see that I've got two different variables. On the x-axis, or my explanatory variable, is the percent taking the SAT. So maybe my individuals here are schools. And I know the percentage of students at those schools that are taking the SAT by looking at the x-axis. On the y-axis, I have the mean SAT math score. So what this tells me is that the percentage of students taking the SAT is trying to explain what the average SAT math score is for each of these schools. And now what we will be able to do is actually look at each individual dot and explain it. And that's exactly what we've done here. So this dot is representing a school in which 27% of its students took the SAT, and whose average math SAT score was 560. Now what we want to try and do is see what's the relationship between these two things. Is there something that is going to be consistent and kind of follow a trend and allow me to make a prediction? And so what we can kind of think about is imagine this whole scatter plot is going to be just filled with hundreds and hundreds of more dots, and you can see that it kind of fits a pattern. And that pattern I'm going to try and smooth out, similar to how we would draw a smooth curve over a histogram. I'm going to try and draw a smooth curve that covers this. And we should hopefully recognize that this is going to be some kind of curve or straight line, maybe some other kind of like sine curve or cosine curve or something like that. I'm going to be able to model this with a mathematics function. Okay, and when I can notice that relationship, I can apply a mathematics function to it, I can start to make predictions, and that's an incredibly powerful tool. So, how do we actually make these scatter plots? Let's go through the step-by-step process by hand. For making a scatter plot, the first thing you need to do is decide which variable goes on which axis, but you know how that's going to go because the explanatory variable is always going to go on the x-axis. We want to label and scale your axes. You may want to use a broken line. You notice that on the example we had up here, the y-axis started near 460, and you've always been told, no, that's shame, we shouldn't do that. But for scatter plots, for bivariate quantitative data, it's acceptable to do, because otherwise all of this space between 0 and 400 is all just going to be empty, wasted space. We're not really looking too much at the verticality relationship here. So there is not going to be a problem with using a broken line when we are making scatter plots. And then lastly, you just need to plot each individual value. So it's simple, it's straightforward, it's just a little bit time consuming. Now the big thing though, what we're really going to focus on is interpreting scatter plots. And what you want to do is look for an overall pattern that's going to help you make those predictions, describe that relationship. Okay? So the first thing we look at is form. Now this is going to be similar to shape. If we were to think about sucks, it's the same kind of idea. Okay? Form is going to be linear, curved, or there may be some clusters in our data set, in our distribution. The next thing we would look at is direction. So both of these things are going to be very similar to shape when we start thinking about that. And then there's going to be strength. Okay, how close do those points follow that form? How close are they together? How obvious is that pattern? The stronger the relationship, the more reliable our predictions are going to be, and the more concisely and coherently we can describe the nature of that relationship. So we usually use the words strong, weak, or moderate, or maybe we would say something like fairly strong, fairly weak, very strong, or very weak. Okay, and if there's still something that's right smack in the middle, we would just say it's moderately strong, moderately weak, something like that. Okay, and then the last thing we look at is deviations, outliers, or any influential points. So this would be similar to unusuals. So you'll notice that we didn't really describe center or spread. That's not what our goal is right now. That's going to come a little bit later. But for right now, what we want to focus really on is these four things: form, direction, strength, and unusuals. Okay, so let's try to do that using these things that we filled in the blank for and try and describe these relationships. And one thing that can be helpful is to, just like we did on the previous page, is to just draw a line that goes through most of the points. Okay, so let's describe the form, direction, and strength here. Well, I can draw a line here that looks mostly linear. How obvious is that linear form? You might think it's strong, you might think it's weak. To me, this actually, we're going to have to work toward like quantifying what this will be, and that'll be in the next lesson. But for right now, what we need is just eyeball it for right now. And I would say this is going to be moderately strong. Okay, so this is going to be moderately strong. We need to also describe the direction. Well, which way is it going? Again, what you can think about is, what would the slope of that line be? Would the slope of that line be positive or negative? And here I can see that this is pretty clearly going up and to the right. So this is going to be a positive relationship. So this is a linear, moderately strong, positive relationship. between whatever these two variables are. Okay, let's do the next one. The next one, this is super obvious that this is going to be like a nice curve. It almost looks quadratic, right? Or partially quadratic. Now, we can try and be really specific with that, but for right now, we're going to be somewhat vague. And I'm going to say this is curved, but all of those points fit on a nice smooth curve. So this is very strong. But now the question becomes, is this positive or is it negative? Well, it's positive for a little bit and then it's negative for a little bit. So that might be something you would want to try and describe. So where does it start to change direction? It starts to change direction right about here. That's the peak or the vertex. Where is that point? That point looks like it's at 10, 9, maybe, somewhere around there, 11, 9 maybe. So what we would say here is it starts positive and turns negative at 10, 9. Try to be specific. Use the actual points to describe those individuals, okay? Next one. This is pretty clearly a very strong line, except we've got this one weird individual right here. Now that individual looks like that order pair is at 13, 13. So it's obviously positive. It's going up and to the right. It's obviously a straight line, and it's very strong, except for that one weird, unusual, maybe influential point. Okay, so let's go ahead and describe that. We would say this is linear, very strong, and positive relationship, except for the outlier at 13, 13. Okay, and at this point we don't need to worry too much about what the calculation is for an outlier. Okay, just by visual inspection you can see if something is unusual and identify it as such. Next, it looks like we've got another outlier hanging out over here at about 19, 13, roughly. And now what's going on here? Well, it's going to obviously be a line, right? It's a linear relationship. It's very strong. Linear, very strong. But is it positive or is it negative? Well, think back to Algebra 1 days. Okay? This is going to be an undefined slope. An undefined slope is neither positive nor negative. It's a vertical line. So instead of actually doing this, here's what we're going to want to say. There's an outlier. At 19, 13. But what about everybody else? What's everybody else doing? Every other individual has an x value of 8. Every other individual takes an x value of 8, okay, regardless of their y value. And that's a good way to describe that verticality. Now, you don't have to worry too much about this. This kind of situation is rarely going to pop up in any other kind of data set, but just to give you an idea of how we can still see different types of data sets and still describe them. Now, before we leave for the day, I would like to go ahead and address the previous example where we actually have some context, because here we didn't describe anything in context because there was none. We didn't have any context for these 4 data sets. So don't forget, always describe in context. Don't talk about points. talk about the values. Identify the X and Y variables by name. Talk about the individuals, the X and the Y variables by name. That's how we describe things in context. Now, let's go back up and describe this distribution of bivariate data in context. Okay? So what is this? This is curved, but it's not like the direction's never changing. It's negative, but it's always staying negative. So it's actually almost somewhat linear at the same time. And what we would actually do is, this is super fun. We had to kind of make up our own new exciting words that don't seem to make any sense. I would say this is curvilinear. And this is actually a legit word in statistics. And we would say that this is a pretty strong relationship. It's pretty obvious what this relationship is. And we would say there is a strong negative curvilinear relationship between percent of students taking the SAT at a school and their mean SAT math score. So this is the academic vocabulary way of saying it. It's the most efficient way of saying it. But really, what does this actually tell me? Well, this is actually interesting. Okay, by saying that it's a negative relationship, it's saying that the fewer students that are taking the SAT, or the lower percentage, the higher their SAT score is. And that might make sense, because maybe a school is only encouraging its very best students to take the SAT to make themselves look good. However, if we have this case where we have a high percentage of students taking the SAT, the entire student population, maybe it's because they were forced to. Maybe it's because the school paid for everybody to take the SAT and students weren't really bought into it and they didn't really care. That's everything that I can start to make these assumptions about, or start to make some inferences about, that is based on data, that's based on the nature of this relationship. I can start to make some inferences about what is really happening and try and start to explain my observations. That's why we want to look at this bivariate data. Okay? Now, by saying it's curvilinear, that tells me even more. It's not a strictly negative relationship to where I say, like, it's always going to follow this negative trajectory. What I can see that it's curvilinear is that it's actually starting to bottom out at a certain point, right? It's saying, like, once we hit about 40% of students taking the SAT, there's not really that much variation in what their main math score will be. So really, if a school is trying to look super good and say, like, hey, we got rock star math kids, but let's push a lot of our kids to take the math test, maybe they only stop at encouraging about 40 to 50%, right? There's not that much change in that from 50% and on. There's not much change in the mean SAT math score. All right, so that will do it for today's lecture about scatterplots and correlation. Go ahead and take a look at the examples that we do and get started on your practice assignment. Have a wonderful day, and I will see you next time.